All right, today we're going to walk through a really fascinating scientific paper. It's one of those that takes the principles of nuclear magnetic resonance and uses them to challenge something we all take for granted, our fundamental understanding of gravity. We're going to treat this like a scientific seminar, breaking down the core physics, looking at the experiments, and exploring the pretty profound questions that come out of it. Okay, so here's our roadmap. We'll start with the foundational principle here, the nuclear magnetic moment. Then we'll see how that can be used to actually generate motion. We'll look at the two key experiments, and from there, we'll get into the really mind-bending implications for gravity and maybe even human biology.
So first things first, to really get what's going on later, we have to understand the engine that's driving this whole hypothesis, the nuclear magnetic moment. So let's start with the basics. You have certain atomic nuclei that, for our purposes, act like microscopic spinning tops. They're like tiny little magnets. Now, when you put them inside a bigger magnetic field, they don't just snap perfectly into line. They try to align, but they also wobble or precess around the field lines. And that predictable wobble is the key to absolutely everything that follows. As you can see in this diagram, that precessional wobble isn't just some neat little quirk of physics. It actually generates its own angular momentum. And of course, from classical mechanics, we know angular momentum is a conserved quantity. The universe demands that this value stays constant, which means any change has to be balanced out by some kind of reaction. Now, this is where we can actually start to manipulate the system. If we apply a radio frequency pulse, an RF pulse, that's tuned to that nucleus's specific resonant frequency, what's called the Larmor frequency, we can essentially kick it. We can knock its magnetic moment out of alignment with the main field and bump it up into a higher energy state. Okay, so we can manipulate these microscopic nuclear moments. The next logical question is, so what? Can we actually translate that tiny, microscopic push into a macroscopic, observable motion? Well, that's the first major claim of this paper. And this question is really at the heart of the first experiment. See, in a normal, stationary object, you've got all these precessing nuclei, but their angular momentums are all pointing in different directions, so they basically sum to zero. It all cancels out. But what happens after you hit them with that RF pulse? If the new sum is not zero, the law of conservation of angular momentum demands a reaction. And the hypothesis here is that the object itself has to rotate to balance the books. This leads us directly to the spinning disk experiment, which was designed specifically to test this very hypothesis. Could they really make a solid object spin just by hitting it with a radio wave? So the procedure, as you can see here, was planned out very carefully. They chose a bismuth disk. It has a specific crystal structure, and it's good for NMR. They put it in a magnetic field, hit it with a strong electrostatic charge to make sure they were isolating the nuclear effects from any electron interference, and then they pulsed it with radio waves, fully expecting it to move. Here's a little schematic of the setup. It's pretty simple, but really elegant. And the result? Well, it was observable. When the RF pulse was powerful enough, the bismuth disk made a distinct partial rotation. Sometimes it was really obvious, other times it was barely perceptible, but the crucial thing is, it moved. And just like that, the initial hypothesis was confirmed. This wasn't some theoretical curiosity anymore. They had actually demonstrated a direct conversion of radio frequency energy into mechanical work. It was a validation of their whole understanding of how to manipulate nuclear angular momentum on a big picture, macroscopic scale. Now, with this really crucial experimental proof in hand, the researchers take a monumental leap. They basically reasoned that if this principle of conserving angular momentum works for a small disk in a magnetic field, well, it has to hold true for all matter within the biggest rotating system we know, planet Earth, which has its own massive magnetic field. And this slide really lays out the paradigm shift they're proposing. On the one hand, you have conventional gravity, a fundamental force. It's linked to mass. But this paper suggests a totally different origin story, that gravity is actually a compensatory force. It only exists because the Earth's rotation is constantly forcing all the atomic nuclei within its magnetic field to adjust to conserve their angular momentum. Gravity is the force that makes that adjustment happen. This diagram does a great job of illustrating the proposed mechanism. So, look at a particle rotating with the Earth. Its velocity vector is always changing. Now, to keep its angular momentum constant while its velocity is changing, the particle's radius of rotation also has to change. It has to adjust. And this required change in radius shows up as an inward pulling force, which they've labeled here as F. The paper then boldly identifies this force as what we experience as gravity. So, Any good new theory has to make a testable prediction, right? And this one makes a prediction that is deeply, deeply disruptive. If this is all true, an object's weight shouldn't be constant. It should actually change depending on how it's oriented relative to the Earth's axis of rotation. So, to test this, they came up with a really simple but clever experiment. They used these thin, rectangular sheets of zinc and titanium. The idea was that the asymmetric shape and the specific crystal structures of these materials would interfere with the uniform alignment of atomic moments from Earth's rotation. And that interference should result in a different net force, and therefore a different weight, depending on which way the sheets were facing. The result they recorded was, well, it was astonishing. By simply weighing these sheets and then just changing their orientation relative to the Earth's rotation, they saw a weight difference of up to 2 grams. Now, a 2-gram difference might not sound like much, but in physics, that's an earthquake. Weight is supposed to be the product of mass and the gravitational constant. To have that value change just based on orientation, without changing the object's mass at all, is a profound anomaly. It fundamentally challenges our entire understanding of gravity. As you can imagine, a result like this just opens up a cascade of startling questions that could redefine not just physics, but maybe even biology and space exploration. These results really force us to ask some huge questions. Is gravity fundamentally tied to rotation? When an astronaut is in microgravity, are they really experiencing an absence of gravity? Or is it an absence of the specific rotational velocity and magnetic field that our bodies are tuned to? And if we can influence these nuclear moments with RF pulses, could we one day actively modify an object's weight? And maybe the most pressing implication here is biological. We all know astronauts suffer some pretty significant health problems in space: bone density loss, cardiovascular issues, and it's all been attributed to the lack of gravity. But what if we've misdiagnosed the problem entirely? And this final takeaway from the paper is just so provocative. It suggests that what our biology truly needs isn't the pull of gravity itself, but the constant influence of Earth's magnetic field on the atoms inside our bodies. And that leaves us with this profound question for the future of space travel. Should we be trying to engineer artificial gravity, or should we be building ships with robust, Earth-like magnetic fields? The answer could change everything.